So today I start chapter 6, the Laplace Transform. Now this is an integral transform. It's used to solve differential equations and also to model so many things in engineering fields. If you study electrical engineering, you will see that a lot. And those who study mechanical, chemical, aerospace, and maybe others, they will see that in like a course on control science or control engineering. But anyway, so let's start. So what is it? So we have some space of functions, say, and the other one is also another space of functions. So if we can define something like a transform, like a linear function, say. So both are vector spaces. If we can define some linear function, say L, which is one-to-one, which means it has an inverse. Then, so it takes a function here, say f, and into f, say something, into f, say. So it's like this f here goes to f here and back. Okay. So this transformation takes some function f, small f, into capital F and back. And it's linear. So L of f1 plus f2 will be f1 plus f2. And L of some constant times f will be k. So it's linear. Now, what we do here is this. In this space, which is like space of functions, say infinitely differentiable or something, and we have a differential equation here. If we can bring this differential equation, which is something in this world, to some kind of equation, which you will see is an algebraic equation in this world, and solve it here, then back to this world. So maybe here in this world, it's much easier to solve it than in this world. And you will see that it is in fact much easier to do it here. So that's the process. You have something here, an equation here, differential equation. Using this transformation, you bring that equation to this world, and in this world it becomes like an algebraic equation, and you solve it here, and then back to this world. So your solution here will be some function like this. Then you apply L inverse. L inverse is also linear. You apply L inverse to f, and you will get f. Okay. So this is the philosophy or the theory behind it, behind any like transformation. Now, well, this Laplace transformation or other transformation, it can be applied to any function here. I mean, first we have to choose a specific space for that, but anyway, that's like behind the scenes. So, and then we have to find the Laplace transform for many functions. And because it is one-to-one, we can gather them in a table, for example, like there is a table of Laplace transform in your book, and using that table, there is no need to know L inverse. Because if you have a table for this, you can just look at f's here and find f. Look at this f here and find this f. So using a table, you can do everything. There is no need to know formulas for that. Well, anyway, we have to define it, and we have. I have to show you what this transformation does to a differential equation. In fact, how does a differential equation change into like an algebraic equation? Say, okay. So let me erase this and define an integral transform. So an integral transform is something like this. This K is called a kernel. Look at this carefully. I don't know if you have seen an integral like this before, but so this integral on the right side, this integral is on t, right? But this function is a function of two variables, s and t. So this s with respect to this t is like a constant. So in the end, when you evaluate this integral, you will get an expression which has s in it. So that is in fact what we call fs. Well, you can see that this integral transform in fact is linear, right? So let me show you that this integral transform and any other integral transform is some kind of linear. So if I call this integral transform if I say I of f is this big F, let's call it I. Then what is I of, say, f plus g? Well, that is alpha, beta, k, st times ft plus gt dt, and this splits. If you have a nice function, it splits ft dt plus integral alpha beta kt gt dt. And this is in fact f s g s. So I of f plus g is in fact fs plus gs, or this is in fact I of f, right? And this is in fact, this one is I of g, right? So I of f plus g is if plus ig. And the other one is also easy to show, even easier than this. So if I multiply this function by I of, say, some constant c times f, that will be integral alpha beta kst cft dt. The constant, you can write it outside, alpha beta kst ft dt. So that is c fs, or it is c I of f. So both conditions are satisfied by this transformation, by this what I call it I. So this is in fact a linear transformation, say, or a linear function, or whatever you call it. Anyway, now, so that's an integral transform, and with changing this, by changing the kernel, we get different integral transforms. Now, one of those integral transforms is the Laplace transform. So let me erase all this and define the Laplace transform for you. So, the Laplace transform. Okay, so the Laplace transform is in fact a transform which the kernel of this transform is e to power minus st. And alpha, 0, beta, infinity. So Laplace transform of a function f is from 0 to infinity, e to power minus st, ft dt. And like the other ones, I can write this as fs. Okay? So, the Laplace transform is an integral transform with the kernel e to power minus st, and the bounds are 0 to infinity. Well, let's see. This e to power st is a function of two variables s and t, say in some function space. So then this remains fixed. But this is the function that f. So this whole machinery is applied to this function f. Let's see what happens if I apply to one of the functions that we know. Something that we have used a lot, and that's the exponential function, right? So the first example, let me find the Laplace of e to power, say, at. Okay? So that is integral 0 infinity e to power minus st e to power at dt. So that's integral 0 infinity e to power a minus s t dt. Okay, so that is in fact 1, well, that's in t 1 over a minus s e to power a minus s t from 0 to infinity. So that is 1 over a minus s e to power a minus s times infinity minus e to power 0, right? Okay, so let's look at this one. If this is negative, f minus s is negative, then it's e to power negative infinity, and that's 0. I need this to be 0. Otherwise, it's infinity, so what I have found nothing. So how could this be? This a minus s should be less than 0, so this means that s should be bigger than a. So this is in fact the condition that we have here, that s should be bigger than a, and if that happens, then this becomes, let me write it here, so this becomes 1 over s minus a. You see there's a negative here, so I apply the negative, that's it. So that's 1 over s minus a, and that's my f s. That's my fs. So, well, that was very easy, except I need that s to be bigger than a, so that's the condition, the s should be bigger than a. So let me erase this and write it here. So I found that Laplace transform of e to power at is 1 over s minus a, given that s is bigger than a. So As you see, this left side, we have e to power at, that's a transcendental function. On the other side, we have just a simple, the simplest, say, rational function. So that's good news, in fact, because such a complicated function and transcendental function, when we applied the transform, we got perhaps the simplest rational function. Okay. And that happens to other functions. This really happens to other functions. Let me try to find the Laplace transform of some other functions, especially the ones that we need, like what, sine, cosine, and things like that. So let me erase this. Another example. Let's find the Laplace transform of sine beta t. Okay. So that is integral 0 infinity e to power minus st sine beta t dt. Well, if you recall from Calc 2, this is not a simple integral. In fact, that is a complicated integral to find. But well, let's try. So I have to use integration by parts. I can use integration by parts here or on this one, because they have the same weight, let's say. So that is integral 0 to infinity of sine beta t times d of e minus st dt is minus 1 over s e to power minus st. So the derivative of this, or d of this, will be this, right? So it's derivative of there, so that's minus s times 1 over minus s, and that's 1. Okay, so by that gives me minus 1 over s e to the power minus st, and this goes from 0 to infinity, say, and times, this times sine beta t 0 infinity minus integral this one 0 infinity minus 1 over s e to the power minus st, and that is cosine derivative of this. So this beta cosine beta t dt. Well, let me. No, that's okay. So let's say this one for infinity, that's minus st. Well, s is positive, and that will give me, that's for t. So that's minus infinity, and that's 0. This is a number between -1 and 1, so that's 0. And at this end, sine of 0 is 0. So this guy here is 0. This guy here is 0. So I'm left with that, which is 1 over, or beta over s, say, there's a beta here and s here, integral 0 infinity of e to the power minus st cosine beta t dt. Okay. So again, we have to do it again. So e to the power minus st dt, so this is in fact beta over s, integral cosine beta t d of minus 1 over s e to the power minus minus st, and from 0 to infinity, and so this will be, again, we have, let me keep track of what I'm doing. So that's beta over s, and that's minus 1 over s e to the power minus st cosine beta t from 0 to infinity minus integral minus 1 over s e minus st derivative of this, which is minus beta sine beta t dt from 0 to infinity. Okay? So, well, let's see. Let me be careful not to make some silly mistake. So, let me double check and see if minus 1 over s correct. So that's correct. And minus 1 over s derivative of this beta cosine, that's correct. Minus minus to plus. And that's beta over s e minus st. Then I have this thing here. So I have minus this times this, the beta over s outside, and in infinity, or 0 to infinity, and that's minus minus minus. So that is in fact minus. And let's evaluate this thing. Infinity will give me 0 here, no matter what this one is. 0 will give me 1 over s. So this is, this guy here, is minus 0, then minus minus, that's plus, in fact. Plus, when I put 0 here, this cosine 0 is 1. E to the power 0 is also 1, so I will get 1 over s. I will get 1 over s. And this one is, so let me erase this and write everything up here. And I'm finding that. So I have beta over s. The first one, I have a 1 over s here. And this guy here is minus minus minus. Integral beta over s. And what do I have? Beta over s e to the power minus st sine beta t dt 0 infinity. Okay. Well, let's hope I haven't made a mistake, because I erased everything. And so I'm just doing everything on this whiteboard. So let's expand this thing. So I have beta over s squared minus beta squared over s squared integral 0 infinity e to the power minus st sine beta t dt. Now I have this thing here. So this equals something which has the same expression. So if I bring this to this side, I will get 1 plus beta squared over s squared times integral 0 infinity e minus st sine beta t dt. So that equals beta over s squared, right? So this integral, in fact, this integral equals, so this integral, let me not write it, equals this divided by that, beta over s squared 1 plus beta squared over s squared. Let's multiply by s squared both numerator and denominator, and that will give me beta over s squared plus beta squared. Okay? And I think this is correct. Let me then check. I can't find that. table. There's a table in your book which you can you should use it anyway. Sine, yeah, that's correct. So, and we assume that S is bigger than 0. Otherwise, this wouldn't give me 0 when applying infinity. So I'm assuming that this is bigger than 0. Now, so let me write this thing over there. And instead of beta, let me use omega. And then omega will be omega over S squared plus omega squared. Right? So I found that. First of all, this, as you see, sine omega t is another transcendental function. And the Laplace transform of this amazing function is, in fact, nice, not so simple, but a very nice, say, rational function. So that's what I mentioned. So maybe we can make things easier in the other domain. Now, in engineers, especially electrical engineers, they like to call the other space the frequency domain. So they call this one time domain and the other one frequency domain. Remember, I had this thing, and then L goes from here to here. They say that this is like the time domain, and this is the frequency domain. Well, you can see this omega is frequency, and omega is here. I can find the Laplace of cosine also, cosine omega t, that's also frequency, and it has omega. It's the same thing in the denominator. It's the same. That's one reason I think they use that terminology for the other space, frequency domain. So this is time domain. This omega is not changing here. Omega is not changing. You fix omega and time changes. So we have sine omega t here. You have sine omega t. Omega fixed, t changes, and this guy here goes to what? This guy here goes to omega over S squared plus omega squared. Now here S is like fixed in a sense. I mean, omega can change now, and based on the change in omega, you can discuss and talk about, say, stability of the system and things like that when it comes to control systems or electrical systems. And you will see if you study those things, those areas, you will see that in those courses that you take. And perhaps the first thing they say that is it's called frequency domain. Okay. But for us, it's just another function space, right? So this is one function space, this is another function space, and it seems that this transcendental function, when we apply this transform to this, gives me a simple rational function. Well, you can find a Laplace of cosine, but let me write that for you. Laplace of cosine is cosine omega t. Laplace of cosine omega t, in fact, is S over S squared plus omega squared. Let me double check. It is S, yeah. And there are also two other functions which we need. One of them is this. Remember, e to the power alpha t cosine. Let me write omega t again here. And this is, well, let me check here. E cosine is S minus alpha. S minus alpha. Right, S minus alpha, S minus alpha squared, plus omega squared. t sine omega t. You can guess why this happens, because there's e to power minus st times this. So basically you are doing the same integration and you have to do it twice. Well, don't bother. I mean, we have this in the table, so and the sine will be simply omega over that. Yeah, omega over the same thing. Okay, so now you can look at the table and see a Laplace transform for other functions, and also some functions that we will discuss in the coming lecture. So it's amazing that this function, when applied to, this transformation, when applied to functions which are not continuous, like a pulse, say, it gives me an amazing. So the transform is like a very nice function, and most of the application comes when you have a forcing function on the other side of the differential equation, which is not a nice function. It is like a discontinuous function. It's like a pulse. It's like something. So we will see that. We will see that table, in fact, has lots of other transformation, especially for discontinuous functions. So let me now see what happens to derivative of a function. So let's find the Laplace of, so let's say we have a function y, right? So L of y, let's call it this one, right? Now how about yt? What is this? This is where you see magic happening. Okay, let's find it. So this is integral 0 infinity e to power minus st y prime t dt. Right? So what does integration by part give me? Well, it's right here, right? Y prime dt. So that is in fact integral 0 infinity e minus st d of yt. Right? This is d of yt. So that is in fact e to power minus st yt from 0 to infinity minus integral yt d of e to power minus st, right? From 0 to infinity. Okay. Well, let's find this one first. This is in fact yt over e to power st from 0 to infinity. And this one is minus s, so I have an s here. The derivative of this is minus s e to power minus st, minus is plus 0 infinity e to power minus st yt dt. Okay? So here I have this thing. Well, let me write infinity for this t. I know I have to write limit. Oh, that's something like that. Okay. So this, in fact, this is limit as say a goes to infinity of y a e to power s a, say. Right? When t goes to infinity, just put some a here. Well, I can just use t. Why should I use anything else? So let's just write t. So t goes to infinity, yt over est. Minus y0, in fact. Because e to power 0 is 1. So that is for the first part. The second part is plus s. What is this? It's this thing. That is Laplace transform of yt. So that's s times ys. S times ys. Okay? S times ys. So, well, y at 0 is okay. That's not bad. What about this one? I don't like this. Remember when I was finding Laplace transform of sine? Well, it was fine. I had something like this. I had, in fact, sine beta t over e st, right? When t goes to infinity. And I said, look, this is something, when t goes to infinity, I don't care what sine is. Sine is a function between -1 and 1, so it is bounded. And this one goes to infinity. So, a number between -1 and 1 divided by a number which goes to infinity, that is 0. How about this? So if this combination of this goes to 0, then the Laplace transform really works well. So this really applies to functions that have this property, that yt over e st in fact goes to 0. And that is in fact a theorem in your book that says the Laplace transform really applies to not just any function. If this is not in 0, then things are not so nice. So let's assume that this goes to 0. And in fact, for the functions that we are dealing with, this yt it doesn't go to infinite. This yt is like finite in a sense. At least since time doesn't go to infinity, so it just stops somewhere. So we can say that this is really 0. It goes to 0. So what happens? Let me erase this and write the result here. So the result is, in fact, s times Laplace of yt minus y at 0. Right? Or since I use this capital Y, that is s y, s minus y at 0. Y at 0 is a constant, just a number. So it is, in fact, it's just amazing that the derivative, just look, derivative changed to what? This prime and gave me an s here. One derivative gave me s. You will see that another derivative will give me another s. So let's find Laplace of y double prime. So what happens to y double prime? Laplace of y double prime t. So this is in fact integral 0 infinity e to the power minus st y double prime t dt. Again, the same thing. This is y double prime, so I have 0 infinity e to the power minus st d of y prime t, y double prime, 1 primes just goes away. And that is again, like the other one, will be y prime t over e to the power st from 0 to infinity. Again, I assume that this goes to 0, minus y prime at 0, right? Plus, again, it's similar to that, 0 infinity, except I have e to the power minus st and s here, y t dt. Y prime, sorry. Okay? So it is minus s, and so on, because that's the derivative of this. So what do I have here? I have, what is this? I have it here. This guy here is in fact Laplace of this is Laplace of y prime. That's Laplace of y prime, right? So assuming that this goes to 0 again, assuming that this is nice function and divided by st, this is finite, divided by infinite, that's 0. So I have this situation. So this is in fact s Laplace of y prime t minus y prime at 0. Okay? But I know this one, y prime t, so let's write it here. So it's s times this, s L of yt minus y0 minus y prime 0. And as I said, something magical happens. And I will get this squared L of yt minus s y0 minus y prime at 0 or s squared y at s y0 minus y prime at 0. Okay. Well, you might guess what happens to y n t with n derivatives. Well, we usually don't have more than 2, but I can write the formula, the general formula for you. So the general formula will be like this. You can continue this way, and by induction you can say, okay, if I have n here, is it double? 2 minus s blah blah blah. So it should be Sn yt minus Sn minus 1 y at 0 minus Sn minus 2 y prime at 0 minus dot 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 dot, and the last one will be y n minus 1 at 0 without any s. Okay? So by induction you can find this. Now what is good about this? If the initial conditions, these are initial conditions, right? Initial conditions, if the initial conditions are 0, if all of them are 0, then we get this. So let's erase. If the initial conditions are all 0, then L of yt, which is just simply s L of y, L of y prime t, and this is y prime. Y double prime t will be s squared L of yt, but there's y0 blah blah blah, but I assume that they are all 0. y1, 2, 3 t will be s3 L of yt, right? And what happens to this? L of t plus b y prime t plus c y t, assuming the initial conditions are all zero. And remember, L is a linear function, so a linear function distributes over addition, and also the constants, and A, B, C are constants, A, B, C are constants, or just real numbers. So this will be A S squared L of yt plus B S L of y t plus C L of yt, right? So if I factorize the L of yt, if I factorize L of yt, this becomes, this guy becomes A S squared B S plus C times L of yt. Okay. Well, some of you might, well, when you see this, you say, gee, this looks like a characteristic equation, right? Or when you solve the second order differential equation, when you solve with the constant coefficients, that's the characteristic equation, right? Yeah, that is, in fact, it looks like that characteristic equation. But what is it? What is it good for? So let me write the differential equation here. So example, so let's say y double prime plus 5 y prime plus 6y, and that equals, that's it, 1 minus, so let's say e to power 2t, right? And initial conditions 0. Okay, so when initial conditions are 0, you don't worry about those extra things. So let's apply Laplace. This one I know, this is s squared plus 5s plus 6 times Laplace of yt. On this side we found that this is 1 minus s minus 2, right? 1 over s minus 2. Okay? So, this gives me L of yt is in fact this, or divided by this. So I have s minus 2 times s squared plus 5s plus 6. And since I know Laplace has inverse, and the inverse is well defined, and L inverse is amazingly nice, that is in fact yt is L inverse of this function s minus 2 s squared plus 5s plus 6. Okay, that's it. So just remember, if you wanted to solve this using methods of previous chapter, you had to find general solution for that, complementary solution, and then particular solution for the e to power 2t, and then put them together. But if I can find this, I have the solution, just like that, boom. And remember, if even with these being 0, you had to find the general solution with the particular solution included. Then you had to apply initial conditions, right? including the particular solution, you have to apply initial conditions. So this makes life easier. You immediately find the answer if you can find the Laplace inverse of this without even doing all those things, like finding a derivative and applying initial conditions, blah, 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 blah. Well, anyway, no, some students don't like it because they say, gee, finding this is hard. So what you have to do here, which I will explain next time, is you have to integrate this somehow, or the inverse. So you have to use a partial fraction. So that partial fraction, which is something some of you don't like, maybe. So yeah, you have to practice your partial fraction techniques. So next time I will tell you how to find Laplace inverse of this thing. Okay, so see you next time.